All right, ladies and gentlemen, we're going to start with a little bit of retrosynthetic analysis review. Now, we got some words here that you may not have heard me say during lecture, but the chemistry involved in either an acetoacetic ester synthesis or a malonic ester synthesis is all chemistry we have studied so far. What you need to look for in your target molecule is one of two things: a derivative of acetic acid, so some kind of derivative of acetic acid, or a derivative of acetone. Acetic acid, or a derivative, or acetone. And in both cases, you'll be having a target molecule that has two new groups on the alpha position of either acetic acid or acetone. It'll be the same two new groups. It'll be the same groups. What am I trying to say? There'll be two new groups on the same alpha carbon is what I was trying to say. So what we're looking for is one of those two things, and I found this one, and I'm going to highlight it. There's the carbonyl of acetic acid, and there is the alpha carbon with two new groups on it. And just a heads up, it's a malonic ester synthesis that gives a derivative of acetic acid. And on your test, it will be a malonic ester synthesis. I'm not going to say it again. So what we have here is our target. It's not acetic acid, but it's a amide with a D derivative of acetic acid. So you need to recall the reactions you know to make amides. And by far, the most popular one is using a nucleophile that's an amine to attack an acid halide. And what we're going to do here, oh, why not? Yeah, phenyl and phenyl. So you now have two new target molecules. Now, what kind of reactions do we have to make amines? Your limited knowledge now comes from chapter 16, where you made imines or enamines and reduced them to amines. If this is the case on your test, please employ that method. You'll learn more methods for amines when we do the amine chapter, but you don't need more methods. What we have right now is this molecule here coming from, sorry, watch how you word that, coming from, and the best way is to have like benzaldehyde and ammonia. They will react to make an imine, which is an N double bonded to C, which is easily reduced to an amine. And after this, we're almost done with the carbon portions of that retro, the blue, because this comes from benzyl alcohol. And that you can put a circle on because it's on our list of molecules you're allowed to start with. Benzyl alcohol. And let's do the retro over here. Acid halides come from carboxylic acids. That's the only way we know how to make them. One, two, three, four. Okay. This is the real malonic ester target molecule. This is what I said earlier. This is acetic acid with two new R groups on the same alpha carbon. This is the malonic ester synthesis target. It came from a malonic ester. Oh my. Why did I say oh my? Because malonic acid is one of the dicarboxylic acids, and it is the second one in oh my. So oxalic acid has 2 carbons, malonic has 3, and it's a diester of malonic acid. Why do we need to have 2 esters? It's because if we have 2, well, let's do it. Oh, it looks the same on both. There's malonic acid. Here's our new groups. We have CH2, CH2, F, and CH2, CH2, CH2. So 3 times. If we have an ester here, then this alpha position is alpha to 2 carbonyls. And we learned a new pKa, if there were H's there, is 10. That makes it very nice to do synthesis. You can make an anion on a carbon with a pKa of 10. That's why we learned this malonic ester synthesis. This is the diacid. And the protocol that makes the diacid into the monoacid is called saponification, acidification, decarboxylation, if you're talking about the diester. And so here we are. And I just copy this molecule up here. You have to have esters here, or else the pKa of the molecule is less than 5, and you will only be doing acid-base chemistry on the acids. So methyl esters are nice. And, I'm going to jump the gun a little bit and do the forward synthesis here. The protocol to get from an ester to an acid involves saponification, which will generate 2 carboxylates, and then acidification, which is basically just saying protonation. It just has a better sound to it. Saponification followed by acidification, followed by a thing I've threatened to cover in more than one lecture today, or this semester. I don't know what happened there. I just don't know. This machine, it loves doing this to me. I don't even know. Oh, there we are. It just loves doing. Where are you? Where am I? Right there. There. Oh, that's called decarboxylation. And all you have to do is heat a molecule that has a carboxylic acid beta to any carbonyl. And this surely qualifies. There's a carboxylic acid on the left, and there's its alpha position, and there's another carbonyl beta. Maybe we'll do a quick covering of that mechanism later. It's decarboxylation. So the rap song that goes with these three things is 1, 2, 3 equals saponification, acidification, decarboxylation. There you go. It's got a nice ring to it. And this is a malonic ester. Malonic ester. The beauty of the malonic esters is they give us a nice way, easy access to these bonds from the alpha position. Because the anion here is easily made using acid base. The anion here is easily made using acid base from its conjugate acid partner. And its conjugate acid partner has a proton there. Why not blue? Yeah. pKa 10. That's the beauty of this whole synthesis. And we'll take advantage of the beauty of this synthesis again, because this also comes from an anion that is easily generated. And what are we doing here? I don't know. Let's see how this goes. Oh, I forgot to say the other piece that reacted. I was so excited about the synthesis. Well, we'll come up with the two pieces that have to react with these anions. Here, the piece that reacted with the anion in an SN2 fashion was Cl, CH2, CH2 phenyl. Here the piece is Cl, CH2, CH2, CH2 phenyl. And they're just good old SN2 reactions. Anion, backside, attacks the carbon with the leaving group, you make the bond. And this baby right here comes from its conjugate acid up here. What can you do? Conjugate acid having no anion here. No lone pair there, but a second H. Just in review, the pKa of these species is 10. Most certainly, you're going to be using that pKa on your test multiple times. Okay. Make sure you know they're both attached right there. Right. Okay, we are not done. These chloro species have to be made from benzyl alcohol, and this one has one more carbon than benzyl alcohol, and this one has two more carbons than benzyl alcohol. So you're not done with the blue pieces, the dark blue. We'll be done soon, though. We're going with the light pink retro arrow now. And that comes from HO, CH2CH2F, which comes from what? Sorry? I'm thinking about the epoxide from this one where I need 2 new carbons on benzyl alcohol. So hold that thought. This only needs 1 extra carbon, and that would be a formaldehyde, CH2 with a Grignard, BRMG. BRMG. And the formaldehyde's 1 step away from an alcohol. Redox. Alcohol is the reduced version. Aldehyde's the oxidized version. Circle the alcohol. It's an alcohol or a diol of 3 carbons or less. I'm just reciting what's up here. Saturated alcohols or diols of 3 carbons or less. So you've accounted for that carbon. Now we got to account for this coming from something looking like benzyl alcohol. And I don't know, we'll go that way. I don't want the page to get much taller. It's really shrunken down for you guys. That comes from that. Yeah, I should have just copied it. How about draw it? Comes from, you guessed it, benzyl alcohol. The one with 3 carbons is a little higher on the screen. This one, I think we'll sneak it to the right here somehow. Crossing retro arrows, not a fan. I don't know how I can avoid it though. Uh-oh. Having serious artistic issues here. Yeah, to there, to there. Yeah. How's that? Not bad. How about the old the OH up there? Once, twice, 3 times. Take it down so my page doesn't get too wide either. Although I do have to remember, well, I don't need anything down here. Got to count for that. I have enough room up here. Good. Let's see. Hey, this is where I was talking epoxide. These 2 new carbons are new, and there's benzyl alcohol's carbon. So epoxide time. Plus, why don't we just say BRMG? There. And we've made that already. I don't have to show it again. But we have this comes from ethanol. Well, really it comes from the alkene, which comes from ethanol. Oh. Ethanol. Circle it. We were doing the forward steps on the same page, but we have to account for, well, we've already done that. I'll just go to, I'll do a little retro in black here. Just say it goes to star, BRMG benzyl. BRMG benzyl came from that. That's the same place. And now we got to do our Malonic ester, which is, guys, this is just what you need on your test. You're going to come back to this molecule. I won't mention that I already gave a huge hint about that earlier. So you will be copying, well, not copying, you can't copy. You'll be using from your memory what we're doing right now. Esters come from acids. Esters come from acids. It has to be malonic acid. Malonic acid is 3-carbon diacid. Comes from a 3-carbon diol, which you can circle, because it says you're allowed to do a 3-carbon diol. Once again, it's just redox chemistry. And we'll do all of our syntheses steps in red. Big picture. Oh, it is a big picture, isn't it? Can't even get it on one page? Wow, that's brutal. Okay, as close as we got. Okay. Why don't we just take the parts we can see and do those? Oh, that's huge now. A bit overzealous there. Okay. How do I make a diol into a diacid? The answer is very simple. Chromic acid oxidation. Somebody tried to write chromic acid on the arrow last test. They got partial credit. Why did they only get partial credit? Because you have to know how to make chromic acid. You can't buy chromic acid. So one of the nice ways is chromium 6 oxide, sulfuric acid, water. 3 ingredients. You can write AQ instead of H2O. To get from the diacid to the diester, couple options because I chose a methyl ester. You could use diazomethane, or you can use the more general one that works for any ester. Fischer esterification. Little heat. If I don't see the heat, I will not get upset here. But I need alcohol and strong acid catalyst, either sulfuric or paratoluene sulfonic acid. pKa 10 on the next one gives us a big clue. The best thing about this synthesis is this step right here. You can achieve that desired reaction with the cheapest strong base you can buy. It's dirt cheap. Sodium hydroxide. And you've taken the H off. The next step, you just have to say, I need to mix these two things. So I think because I've drawn it this way, if I just say these two come together to make that, and that's all you need to show me. Bring those two together and make this malonic ester target. Okay. Where'd that come from? Well, it came from here. What's it going to become? It's going to become its conjugate base here. Switch to orange so we can keep score here. NaOH again. It's also the best step in the synthesis. pKa 10 again. Why the synthesis exists, so we can do simple acid base on a carbon to get there. And then you made the anion, which is going to have to react with that species to give the thing above. This is starting to get a little tricky now. And I'm just having trouble seeing how to do it. I think a good way is to draw an arrow up here and have this thing meet in with the arrow. How's that? That's not bad. What do you think? That says to mix them, doesn't it? This comes together with this and they meet and become there. How do you make an alcohol into an alkyl chloride? Same way you make an acid into an acid halide, which we need later. SOCl2 pyridine. Yeah. Now, instead of doing a Cl, we're doing a Br here. There is no SOBr2 pyridine equivalent that's reliable anyway. PBr3 works well here. You could have done the SOCl2 pyridine down there, no problem. You'd have a chloro there instead of a bromo. Grignards, that stuff seems to never be going away now. And I think most of us know this part. Diethyl ether has to be the solvent. Magnesium metal. And what do we got here? What do we got here? This needs to be made here. And this is not a chromic acid oxidation, although it's an oxidation. If you use chromic acid, you're going to get carboxylic acid. I don't want it. I need the one that stops after oxidizing once. Pyridinium, chloro, chromate. Yes, it's a chromic acid oxidation. No, it's a chromium oxidation, not an acid. And we need a way to show that these two combined to make this one. So I'm going to do this orange thing again. That met up with, oh, this is a little more involved though. A little more involved. They do have to meet up, but that's not the end of it. Step one, mix. Step two, you're going to have an O minus. You need to protonate it. HCl. And I think we're doing okay. How about the bottom of the screen here? How do you get this to lose water? Ethanol is losing water. It's called dehydration. You need a strong acid, either sulfuric or toluene sulfonic. And this one, I really do want to see the heat, because this does take a lot of heat. You're making a pi bond that wasn't there before, endothermic. Peracids make epoxides. MMPP is a nice, reliable, safe one. Here's another mix followed by HCl. One, mix. You're going to get an O minus. Two, HCl. OH. Oops, I don't know why it ended there. Doesn't end there. What's the fix here? What's the fix? It ends upstairs there. There. This just says, you already knew how to, showed me how to make this, which made this right here. This became the Grignard right here. You showed me that. Don't show me again. I mean, it's fine if you show me again. Bless you. Okay. So we got this. And now we got to make, wow. So we already combined these two to make this. And that. This, oh, we didn't show how that became that. Oh, this is getting sneaky in here. Let's go with a light blue. Oh, we already have light blue. Yellow. Don't write yellow. SOCl2 pyridine converts the OH into a Cl. Then we have this piece and this piece. And did we show how to make this piece? Did not. My goodness. We're going to go from here up to there. We didn't show that anyway. We have arrows on our simple. We're going to go basic black. I just NaOH. I did above it already. Oh, I'm going the wrong direction. Yeah, I got my backwards and forwards mixed up myself because they don't have everything showing. Yeah, I showed how to make the anion. This wouldn't become this with acid base anyway. This reacted with this to make this. That's what this says. This with this makes this. So where'd that come from is the new question. That came from the acid base reaction there, which I already showed. Thank you. And this came from making it. Yeah, we already accounted for the forwards and backwards there. And it was kind of a nice segment. Reviewed a lot of reactions that we did this semester. Pretty sure it's complete. And we'll leave it there and start a new segment pretty soon. All right. Adios.